Hello everyone. Today we will discuss few more problems related to shear strength of PSC members. So let's start with first problem. The support section of a PSC beam 100 mm wide by 250 mm deep is required to support an ultimate shear force of 60 kN. The compressive pre-stress at the centroid is 5 Newton per mm square, FCK 40 Newton per mm square. Effective cover to the reinforcement is 50 mm. If Fy is 415 Newton per mm square, design suitable shear reinforcement in the section using IS 1343 code recommendations. So here cross section is given and the required ultimate shear force is given. So that means your beam should support a shear force of 60 kN. The compressive pre-stress at centroid. So you are providing pre-stressing along the neutral axis, that is concentric pre-stress about 5 Newton per mm square. Then FCK 40 Newton per mm square, that is characteristic strength of concrete. Reinforcement cover is 50 mm. Design suitable to shear reinforcement. So shear reinforcement is nothing but you have to design what is the spacing required for the stirrups. Okay. So these are the data which I have it has given. B, width of the beam is 100, depth, overall depth is 250, shear force it is 60 kN, FCP 5 Newton per mm square, FCK 40 Newton per mm square, D. So effective depth, overall depth minus cover, we will get effective depth. So it is 250 minus 50, 200, and Fy 415 Newton per mm square. So Ft, tensile strength of concrete we need to know. So for that we have 0.24 root FCK. You have this in code book. Principal tensile stress in concrete in code book page number 46, clause 22.4.1. you have in flanged members where centroidal axis occurs in the flange, the principal tensile stress should be limited to 0.24 FCK at intersection of the flange and flanged web. So that is 0.24 root FCK will gives you tensile stress of the member. So that we have calculated here. FCK is 40, by substituting Ft equals 1.517 Newton per mm square. So ultimate shear strength of PSC members. So again in same page you have formula. VCO is equal to 0.67 BD square root of Ft square plus 0.8 FCP Ft. So substituting all the values we will get VC value 48.45 kilonewton. So this is the shear strength of the member what we have, but the shear force it need to carry is 60 kilonewton. So the capacity of member is 48.45 kilonewton and capacity required is for 60 kilonewton. So to increase the capacity we need to provide the shear reinforcement. So therefore shear reinforcement is to be provided in the form of stirrups. So let us assume two legged vertical stirrups of 6 mm diameter. So 2 lbs. So to calculate this area of steel, pi d square by 4, since we have two legged vertical stirrups, so we have multiplied it with 2. So for calculation of spacing you have formula in page number 48. ASV, so it's bit change. Yes, we have formula ASV by SV is equal to V minus VC by 0.87 Fy dt. So ASV, area of two-legged vertical stirrups. SV we need to find out. V is 60 which is given and 48.45 is VC. which we have calculated as a strength divided by 0.87 Fy415 and effective depth is 200. On substituting all the values, we will get 353.53 mm as the spacing, but there should be certain limitations to provide the spacing. So for that, if you go to last paragraph in page number 48, it is given the spacing of the stirrups along the member should not exceed 0.75 dt. So that means your spacing should be restricted to 0.75 times of effective depth. So if you do that, 0.75 into effective depth is 200, it will get 150 mm. So by comparing these two values, we need to consider SV equals 150 mm and provide two LVS of 6 mm diameter at 150 mm center to center. This is about shear reinforcement, what we need to provide in the section. Next problem, a double T section used as a bridge girder is made up flanges 1200, that is 1200 mm wide by 150 mm thick. The ribs are 150 mm wide by 1500 mm deep. The section is pre-stressed by high tensile wires of area 4700 mm square located at 850 mm from the soffit of the girder. The initial stress in the wires is 1200 Newton per mm square. If FCK equals 40 Newton per mm square, estimate ultimate shear strength of the support section of the girder. So here you need to find out what is VC. That's it. There is no need of design. So since it is double T section, as we discussed in previous cases also, if we have two flange webs, we need to get width of web as combining both webs. So BW will be 150 plus 150, that is width of two webs, it will become 300. Overall depth is 150 is the thickness of flange and depth of the web is 1500. So by adding 2 we will get 1650 mm as the overall depth of the section, and effective depth 1650 minus 850. 850 is what which is given in the question, that is the cables are located at a height of 850 mm from the bottom or from the soffit. So total it is effective depth will be 800 mm. So pre-stress area of steel is given and initial stress is given. So we need to find out what is the pre-stressing force. 5.64 into 10 power 6 Newton. Then area 1200 into 150 plus, that is area of flange, and 2 into 150 into 1500, that is area of web. So by combining you will get 630 into 10 power 3 mm square. FCP P by A, stresses from the pre-stress on the concrete. By simply substituting the values, we will get FCP is equal to 8.95 Newton per mm square. FCK is given 40 Newton per mm square. FT 0.24 root FCK from the page number 46 of IS 1343. Here it is. Clause 22.4.1. Ft equals 0.24 root FCK. Substituting we will get 1.517 Newton per mm square. So all the values we got. So again by using same formula we are going to calculate the ultimate shear resistance of the PSC member. That is VC equals 0.67 BD root of Ft square plus 0.8 FCP into Ft. By substituting all the values, we will get VC equals 1.204 into 10 power 6 Newton. So it is nothing but 1204 kilonewton is the capacity of that member. Next problem. A PSC beam of rectangular section 300 mm wide by 600 mm deep is pre-stressed by two post-tensioned cables of area 600 mm square, each initially stressed to 1600 Newton per mm square. The cables are located at constant eccentricity of 100 mm. The span of the beam is 10 meter. If FCK equals 40 Newton per mm square, estimate the ultimate shear resistance of the support section uncracked in flexure. So this is also similar one as in case of previous problem. Width of this, but here it is rectangular section. Section cross section is 300 by 600. Initial stress and area of steel is given. We are using two post tension cables of area 600 mm square each. So 1600 Newton per mm square is the stress and two numbers of 600 mm square. So pre-stressing force will be 1.92 into 10 power 6 Newton. FCP P by A. So by substituting we will get FCP as 10.67 Newton per mm square, FCK given 14 Newton per mm square, FT again from same page 46.24 as the root FCK we will get 1.52 Newton per mm square. So from the same page you have the equation to calculate ultimate shear resistance. It is VC equals 0.67 BD root of FT square plus 0.8 FCP into FT. On substituting all the values, we will get 471.5 kN as the ultimate shear resistance or shear capacity of the member. Next problem. A concrete bridge girder of unsymmetrical I section has an overall depth of 1300 mm with cross-section area of 32.85 into 10 power 4 mm square. Thickness of the web is 150 mm and span of the girder is 25 meter. The girder is pre-stressed by a parabolic cable having an eccentricity of 650 mm at the center and 285 mm at the support section. The effective pre-stressing force in the cable is 2070 kN. If Ft equals 1.6 Newton per mm square, estimate the ultimate shear resistance of the support section. So in this problem, there is a small difference is there. So area it is given, overall depth is 1300 mm, it is given, web thickness is given 150, span is 25 meter it is actually. So but you should observe the profile of the cable, parabolic, eccentricity of 650 at the center. So with respect to centroid of the section, it is below 650 mm and eccentricity of 285 at support, but remember here it is not mentioned, it is above the neutral axis, so we need to consider it as below the neutral axis only. If it is mentioned above the neutral axis, then we need to go for above. If it is not mentioned, we need to consider below the neutral axis only. So same here, 285 mm at the support section, so below the neutral axis. At support it has eccentricity of 285 and at midspan it has eccentricity of 650. So now what is the actual dip of the cable? So that is the difference of the cable level from edge to midspan. So overall eccentricity is 650 minus the support eccentricity of 285. So the depth of the cable is 365 mm. So by using that, we need to find out what is the slope. So to find out slope, we will be having first derivative of the parabolic equation, and at support x will be 0, so directly we will get the value slope for 0.0584. Then P is given 2070 kilonewton. area is also given. P by A we will get FCP value, and FT again same page, root 0.24 root FCK. B equals BW and D is 1300. So here, since we are using parabolic cable, you need to add vertical component of the pre-stressing force. That is the only additional thing we need to observe here. So everything is same, 0.67 BD square root FT square plus 0.8 FCP FT root FT square plus 0.8 FCFT plus P sin theta. It has different profile. So other than straight profile, if it is any parabolic or inclined profile, then we need to go for vertical component of the pre-stressing force. So on substituting we will get VC equals 546.73 kilonewton as the ultimate shear resistance of the beam at support section. So next problem. A PSC beam of symmetrical I section has an overall depth of 2 meter and thickness of web is 200 mm. The effective span of the beam is 40 meter. The beam is pre-stressed by cables which are concentric at supports and have an eccentricity of 750 mm at center of span. The force in the cable is 12,000 kilonewton at the transfer stage. FCK it is 60 Newton per mm square. Estimate the ultimate shear resistance of the support section. If the ultimate shear force at the support due to load is 2834 kilonewton and the loss ratio is 0.8, design suitable shear reinforcement using Fe415 steel bars. Area of the section is 0.88 into 10 power 6 mm square. So overall depth of the section is given 2000 mm, width of the flange width of the web is 200 mm, depth is 2000, width of the web is 200, length span of the beam is 40 meters and eccentricity is given 750 mm at the midspan and concentric at support means 0 eccentricity at supports. So slope of the cable, again the first derivative of the parabolic equation, we will get sin theta equals 0.075. So P is given, area is given, we can calculate FCP by P by A. So it is 10.9 Newton per mm square. FCK is given, FT root FCK 0.24 root FCK, we will be having 1.86 Newton per mm square. FC, since we are using inclined profile and loss ratio is given here, you should be aware of that, loss ratio of 0.8, or if it is given there is a loss of 20% of pre-stress, means you need to consider again 80% of pre-stress is there. So 80% of vertical component of pre-stressing force you need to consider. Here directly loss ratio is given. So loss ratio is 0.8 into vertical component of PSC member. In same page 46 you have this equation. You need to add the thing is 0.8 P sin theta. On substituting all the values, we will get Vc equals 1.9 into 10 power 6 Newton, but it should carry 2834 kilonewton. So here 1.9 into 10 power 6 means it is 1900 kilonewton, but it need to carry 2834 kilonewton. So the strength required is more than actual strength, so we need to provide shear reinforcement. So using 12 mm diameter of two-legged vertical stirrups, since there is a huge difference, almost 1000 kilonewton, we will go for bigger size diameters. It is just an trial and error. There is no particular way to select the diameter. So minimum, if there is a small difference, minor difference, you can go with 6 mm. So here we have huge difference of 1000 kilonewton nearly. We are selecting 12 mm diameter of two-legged vertical vertical stirrups as a shear reinforcement. So ASV, it is two-legged vertical stirrups and diameter of pi d square by 4. We will get 226.19 mm square as the area of stirrups. So spacing, go for page number 48, clause 22.4.3.2. you are having the equation, substitute the values, you will get the spacing 153.01 mm. So again in the same page 48, you are having the maximum spacing to be provided is 0.75 times of dt. So effective depth is 1750 mm. So 0.75 into 1750, you will get 1312.5 mm. So by comparing these two, the minimum is 153. So therefore provide two-legged vertical stirrups of 12 mm diameter at 150 mm center to center. So by this, the fourth module, which is design of shear for PSC members, has got completed. Thank you.